Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. We've all heard all sorts of statements made about antennas kind of in passing. As I was considering what I was going to do to enhance my 80-meter antenna, I got curious about the various wire antennas and the stuff I'd heard about them. So I set out to compare 4 different kinds of antennas to see what is what. In this video, I'd like to share my observations as I used the free 4NEC2 antenna modeling program to compare these 4 antennas: the dipole, the folded dipole, the inverted V, and the folded inverted-vee antenna. In each case, I will be looking at the feedpoint impedance, the bandwidth, the best SWR, the radiation efficiency, the gain, the takeoff angle, and the beam width, while at the same time keeping the center frequency and the feed point height the same. I will adjust the leg lengths to provide the best SWR at the center frequency for the nominal feed point impedance of the antenna. Look for the link to the zip file which contains the 4NEC2 design files and the Excel spreadsheet used in this video in the description. I will give a brief introduction to the design files in this video so that you can reuse them at will, but I will not be stepping through how to model the antennas. If you're not familiar with the modeling of antennas in 4NEC2, I suggest that you watch my quick tutorial video. I put a link to it up there in the corner for you. If you have questions or comments, please feel free to add a comment to the video. I honestly do make a concerted effort to respond to every comment. If you find this video helpful, please click on the like and don't forget to subscribe. Now, let's get started with the dipole. I have created a 4NEC design file which allows us to model anything from a straight dipole to an inverted V with any angle that you might choose between the legs. I will be using this design file here. Now, before we begin, we need to be sure that the characteristic impedance is set to the right value. The impedance of a dipole in free space approximates 75 ohms. So let's set it for that. It is very, very easy to forget to change the characteristic impedance when you change from one antenna type to the next. That value is not embedded in the design file. Be sure to double check yourself each time. Now let me give you a quick introduction to the symbols used so that you can use this too. First of all, let's open the file. Now let's open the editor. The first thing that we need to do is make sure our units are correct. This resides on the Symbols tab at the bottom. This design file is set up to operate in feet. Now let's take a look at the individual symbols in this file. On line 1 is the constant used to calculate the leg lengths for a dipole antenna. The standard formula is 468 divided by the frequency in megahertz, which calculates the overall length of a half-wave dipole antenna in feet. We're calculating the length of just one leg, so we use 234 instead of 468. In meters, this is 71.3232. Line 2 contains the center frequency symbol F. This is the center frequency in megahertz. I use this to calculate the lengths of the legs of the antenna. Now you'll notice down in lines 9 and 13 that the lengths of the left and right legs are calculated using the standard antenna formula. It assumes a symmetrical antenna. Now, while leg lengths are calculated on lines 9 and 13, you could choose to enter your own values and not bother with the calculations. This would give you intimate and direct control over the individual leg lengths. In other words, you could design an offset fed antenna. On line 3, we have the height of the feed point of the antenna. Because my tower is 55 feet tall, I always set it to 55 feet, or 16.764 meters. On line 4, I define the length of the antenna segments. Remember, you have wires, and each wire is broken up into segments. So I define the length of the individual segments. Here it is defined as 4 inches, or 1/3 foot, or 0.1016 meters. Next, we have the radius of the wire used for the antenna in feet on line 5. In this case, it's 12-gauge wire, as I mentioned before. On lines 6 and 7, you can define the angle that each leg makes to the vertical. Here we have it set to 90 degrees because we are modeling a dipole. From here on down are all calculated symbols based on the values already entered. Now I'm going to set the center frequency of my antenna to 7.15 megahertz, the center of the 40-meter band. Now we have to jump over to the frequency ground tab and set the frequency there too. Now I optimize the antenna using the optimizer. The variable I'm going to give the optimizer to play with is the frequency, or F variable, which indirectly adjusts the lengths of the legs. When complete, we save the file out with a new frequency value. Next, I will do a frequency sweep across the entire 40-meter band and export the SWR data for our spreadsheet. Now I'll grab the far field pattern so I can see its radiation pattern and efficiency. On this page, we can see the gain, the beam width, and the takeoff angle of the antenna. Over here, we can see the radiation efficiency of 74.78%. All of that data we're going to put into our spreadsheet. Now that I've completed the dipole, let's morph our generic model to be an inverted V antenna. The first step is to change the characteristic impedance to 50 ohms. Now, while the angle between the legs of an inverted V antenna may be anything that works for you, the classic textbook version has the legs at 90 degrees from each other. To accomplish this, we set the angle of each leg relative to the vertical to 45 degrees. To do this, we open the editor and go to the Symbols tab. We change the R angle, which is the angle of the right leg, and the L angle, which is the angle of the left leg symbol values, from 90 to 45. And then we're going to save it under a new name. Done! Now we optimize as before so the antenna has the best SWR at the center of the 40-meter band and save the file with the new F value. We do the same frequency sweeps and data gathering as before. With the dipole and the classic inverted V antennas complete, we can turn our attention to the folded dipole. So what exactly is a folded antenna? Well, think of it as a big loop. We exit one side of the feed line, travel out to the end of one leg, then we make a turn and travel a little distance perpendicular to the first part of the wire, and then make another turn to travel back in the direction of the center, but we keep right on going past the center to the other end of the second leg. At that place, we make the same kind of end of the leg turns as we did at the other end, and now we travel back to the other side of the feed line. This forms a big loop. As said before, I have created a generic antenna modeling file for folded dipole and folded inverted-vee antennas. And this is the file I will be using for this investigation. Now, let's take a look at the folded dipole. To begin with, we have to address the whole topic of characteristic impedance of the antenna. In general, a folded version of an antenna has a characteristic impedance roughly 4 times its non-folded counterpart. Thus, the folded dipole's characteristic impedance is going to be 4 times 75 or 300 ohms. Now, we're starting with a folded dipole, so we have to set the characteristic impedance to 300 ohms. Now, let's open the antenna modeling file and take a look at the symbols. Of course, the first thing that we have to do is make sure that our scaling is correct at the bottom of the Symbols tab. This, like the other design file, is set up to operate in feet. Now, the symbols associated with the folded dipole inverted-vee model are absolutely identical in every single way to the non-folded model we just finished using, with one exception. We added one more symbol, SEP, for separation, which is the distance between the two sides of the folded antenna in feet, or meters if you choose to operate in meters. I have done rather extensive experiments regarding how this variable affects the performance of a folded dipole. In short, the greater the separation, the wider the bandwidth, with the law of diminishing returns heavily involved. Now, let's configure this generic model for our analysis. The first step is to set the value of the center frequency, f, to 7.15, the center frequency of the 40-meter band. It appears that it is already set to that, but nonetheless, let's go over to the Frequency Ground tab and make sure that the frequency is set to 7.15 megahertz there too. Now let's go back to the Symbols tab and make sure our R angle and L angle are both set to 90 degrees because we're modeling a folded dipole. Lastly, set your desired separation by assigning the appropriate value to the SEP symbol. Now I've chosen 1 foot or 0.3048 meters. Now we save our file out with a new name. As before, we optimize the antenna, scan the 40-meter band, export our data to the spreadsheet. With the folded dipole done, we turn our attention to the folded inverted-vee. Now, the characteristic impedance of a folded inverted-vee is around 200 ohms. So we have to start out by changing 4NEC2's characteristic impedance setting to reflect this. Next, we open the 4NEC2 editor and go to the Symbols tab. The only thing that we have to change here is the R angle and the L angle symbols. They are currently set to 90 degrees for a folded dipole. We will change this value to 45. This way, each leg of the antenna will be 45 degrees from the vertical and 90 degrees from each other. And now we save the file with a different name. As before, we optimize, scan, and export our data to our spreadsheet. Now that we've completed all of our simulation and data gathering, let's take a look at the data that we collected and see what we have discovered. Our first stop is going to be the antenna's bandwidth. Now, before we go there, I need to define what I mean by the bandwidth of an antenna so that we're all on the same page. As we scan an antenna in frequency, the reported SWR will change as the frequency changes. If the antenna is tuned properly, the SWR will drop to some value well below the 2-to-1 mark. If we continue to move along in frequency, the SWR will begin to rise again until it exceeds the 2-to-1 mark. So we mark the frequency at which the SWR drops below 2-to-1 and the frequency at which it rises above 2-to-1 again. When I speak of the bandwidth of an antenna, I am referring to the difference between these two frequencies. Well, why an SWR of 2-to-1? No particular reason. I just needed a consistent benchmark so I could compare the performance of various antennas, and I chose an SWR 2:1, which is about 11% reflected power. With that understood, let's take a look at the SWR curves for our particular experiment. Right out of the gate, we have a nice problem to have. You notice that none of the SWR curves rise above the 2:1 mark within the 40-meter band. So we have to choose a different benchmark so that we can compare these four antennas. Now, pulling a number out of the air, let's try 1.25 to 1. Now let's take a look at the comparison chart. It's immediately obvious that the inverted V antenna has the narrowest bandwidth, and the folded dipole antenna has the widest bandwidth. The inverted V is a mere 115 kilohertz between the two 1.25 to 1 SWR points, whereas the folded dipole is more than 2 times that at 258 kilohertz. Bringing up the middle are the dipole and the folded inverted V antennas with nearly identical bandwidths of about 169 kilohertz. Now, I found this to be pleasantly surprising. So maybe the lesson learned here, if you can't put up a dipole and you have to use an inverted V, but you want to have the bandwidth of a dipole, then consider using a folded inverted V. Then there's the whole SWR issue. As you can see in this chart, the best SWR achievable with each antenna at their respective characteristic impedances didn't differ very much. From this perspective, the differences are, well, without importance. But don't forget, the downside of the folded versions of the dipole and inverted V is that you cannot just connect your feed line to them. You must use some sort of impedance transformation, such as a 4:1 balun, in order to get these good SWR readings. Well, what about radiation efficiency? The dipole and the folded dipole antennas sport almost 75% radiation efficiency, whereas we lose almost 7.5% efficiency with the inverted V configurations. The conclusion here is that the inverted V is less efficient at taking the transmitter's power and converting it to an electromagnetic wave which travels to our distant station. Then there's the gain of the antenna. With regard to the overall gain of the antennas, the dipole configuration yields about 6.5 dBi gain. The inverted V configuration gives us about 5.2 dBi gain, a loss over the dipole of 1.3 dBi. Now, this holds true whether we're talking about the folded versions or the non-folded versions. Now, in my mind, this kind of goes along with the loss of radiation efficiency. The inverted V antenna has less overall gain. Next, we have the takeoff angle. So what is the takeoff angle? Well, quickly here, we start in our mental picture with a large ball. This is the Earth. Now, lay a straight piece of lumber on that ball. This straight stick is the horizontal which we speak of. The takeoff angle of our antenna is the angle taking off above the stick from the point where the stick is touching the ball. Now, picture in your mind that this ball resides inside a larger sphere. The signal that you're transmitting is on a course to hit this outer sphere. It will reflect off of the inside of this outer sphere and return to the Earth to be heard by someone over there. The lower the takeoff angle, the further away the signal will come back to Earth. As you can guess, those interested in DX want a low takeoff angle. Now, 4NEC2 gives the radiation angle relative to the vertical. I will convert this to an angle relative to the horizontal for the sake of visualization. The dipole configurations give us a takeoff angle of about 35 degrees relative to the horizontal. On the other hand, the inverted V antenna configurations give us a takeoff angle of about 40 degrees. So the dipole's takeoff angle is 5 degrees lower than the inverted V's, making it a better antenna for DX. But I ask, how much of a difference does 5 degrees going to make? Well, what about beam width? The narrower the beam width, the smaller the area that your RF power is being focused in. Now, when we talk about a directional antenna like a beam antenna or a Yagi antenna, the beam width is very narrow, focusing your RF power in a single direction. As we look at the dipole, we see that its beam width is 45 degrees. On the other hand, the inverted V's beam width is 65 degrees, making it less directional. Now, this might not be a bad thing. It might even be a good thing if you're limited to how you can orient the legs of the antenna. On the other hand, your RF power is being spread out over a larger area, making your signal strength at the receiving end lower. So the folded versions of both the dipole and the inverted V antennas really do not have any real advantage over their non-folded cousins, except the one significant advantage of noticeably broader bandwidth. This is especially advantageous in the lower bands where complete band coverage can be a real challenge. The dipole, whether folded or not, has advantages over the inverted V configuration on nearly every metric. However, not all of us have the trees or poles or towers to erect a dipole antenna. In my case, I only have a single 55-foot tower to hang wire antennas on, so I'm forced to use an inverted V antenna. I can mitigate one of the disadvantages of the inverted V antenna by using its folded version to increase my bandwidth on the 80-meter band. So there you have it. Some interesting stuff here, at least from my perspective. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, Toodle-oots.